He's going to speak on mapping class groups of non-orientable surfaces. Yeah.
Well, thank you very much. I'd like to thank the organizer for the invitation to speak at this conference. I want to tell you a little bit about mapping class groups of non-orientable surfaces. So let me start by recalling the classical mapping class groups. The surface. So you have a surface, say compact, orientable G, then the mapping class group is the set of path components of the group of the orientation preserving diffeomorphisms, right? And this can be thought of as a quotient of the quotient of the orientation preserving diffeomorphism, but a component of the identity is 0, right? So here I have a couple of examples. The mapping class group of the two-dimensional sphere is trivial, meaning that the orientation preserving diffeomorphisms of S2 are connected, and thus Diff is equal to Diff 0. And in the case of the torus, we know that the mapping class group is a classical modular group. That's the reason for the notation in every surface. So I guess these mapping class groups are some kind of groups of symmetries associated to the surfaces, right? So a cohomology is known for these groups. For instance, they're generated by denturists, right? And presentations are very well known. And I'm the kind of topologist who likes to play with configuration spaces and break groups. And in this direction, well, there is a variation variation of the mapping class group that allows marked points. So you think of all the diffeomorphisms of the surface, orientation preserving, which preserve a set of K points, and look at the group of path components that the mapping class group of the surface with marked points. Okay? All right. So there's a lot of features associated with this group. And one of the most important is the so-called Nielsen realization theorem, which so you know that we can project the diffeomorphism to the mapping class group, right? But it's well known that there's no section for this projection. Nevertheless, you can list any finite subgroup of the mapping class group can be realized as a group of orientation preserving diffeomorphisms. This is a theorem with a long history that starts with Den, and it was completely proven in '83 by Farrell. Okay? So he proved that every finite subgroup of the mapping class group can be realized as a subgroup isometrics for some hyperbolic structure of your surface, right? So the mapping class group also acts on the Miller space of complex structures of the surface, right? And you can think of the quotient as the modular space of Riemann surface, right? So in the same work, Kerckhoff showed that this theorem, Nielsen realization, was equivalent to show that every finite subgroup of the mapping class group acting in the Miller space, and the actions by pullbacks of the structure has a fixed, right? This is what he showed in his work, right? So you can do the same in the case of mark points. So you can define the technical space of your surface with K mark points, right? And in this direction, Volcker and Messer and Wolf, they show that well, the same thing happens when you consider the so-called extended mapping class group, the one that considers orientation preserving and reversing diffeomorphisms, right? With mark points. So what they show is that every finite subgroup of this group acting on the corresponding mirror space also has a fixed. So there is Nielsen realization for the extended mapping class group with mark points. All right. So now, what is the use? Why are we interested in this thing? Well, thanks to the work of R. Niels and Granay, we know that the homotopy type of the identity component of the diffeomorphism on a surface. And for instance, in the case of the sphere, case of genus 0, we know that this sphere is homotopy equivalent to SO3. In the case of the torus, we know that the connected component of the orientation preserving diffeomorphisms is homotopy equivalent to torus. So the torus actually rotations have both coordinates, and the inclusion of the torus on the diffeomorphism gives us a homotopy equivalence and the way and his identity component is trivial otherwise for higher groups. So in this case, we can look at the exact sequence that models of that gives us the definition of the mapping class group, right? And if the genus is greater or equal to 2, then passing to classifying spaces, we see that the classifying space of the orientation preserving diffeomorphism is of the same homotopy type as the classifying space of the mapping class group. Right? And that tells us that the cohomology, for instance, the cohomology of the discrete group we're looking at is the same as the cohomology of the classifying space of all the diffeomorphisms. Right? So now, the left-hand side is interesting because it gives us characteristic classes for surface bundles. Maybe we think of smooth surface bundles and for X. Then these are gotten as pullbacks of a universal bundle, the universal surface bundle over the classifying space of the orientation preserving diffeomorphisms, right? And since so whenever we have cohomology classes in the classifying space and a classifying map F, then we get corresponding classes on the base X, right? So this is the cohomology of the classifying space in the case of characteristic classes in this way. All right. So that's one of the reasons the cohomology is interesting. And the cohomology of such groups has been calculated by various people, right? And also by the work of Wurmford, Morita, and Miller, we know that there are classes, even dimensional classes, so that the polynomial ring on this kappa maps to the cohomology of the mapping class group, and that becomes an isomorphism when G tends to infinity. So this gives us the stable cohomology, the stable rational cohomology of the mapping class groups. All right. So what about lower genus, right? So, and I said that this cohomology groups that detect bundles, surface bundles, right? But what happens when G is equal to 1, for instance? Well, there's a very nice approach to calculate the cohomology of the classifying space of the diffeomorphisms of the torus. So again, we go back to the definition of the mapping class group. In this case, it's SL2D. right? And then has two classifying spaces that produces vibration for us, right? And the corresponding cell spectral sequence has a simple term, the cohomology of Z to Z with coefficients in the cohomology of C infinity times C infinity. This is cohomology of twisted coefficient, and that converted to the cohomology of the classifying space of the diffeomorphism of the top. So now, so one has to compute the E2 term first, right? And say that we work with rational coefficient, it's indicated in there. So one nice thing about SL2Z is that so we know that the availability, right? The first homology of SL2Z is C012, right? And the kernel of the availabilization map is a free group on two generators. So an argument using the restriction and the transfer then tells us that the cohomology, the rational cohomology of SL2Z has to inject into the cohomology of S2, which is the cohomology of our weight of 2 right? So everything is in the spectral sequence concentrated in the electron 0 and 1. So this is what the E2 term looks like. Moreover, in degree 0, we're looking at the invariance of the action of SL2Z on these polynomial ring. So again, we're dealing with twisted coefficients, and the way that SL2Z acts on the variables x and y is written here, right? And but in this case, the only invariants are the constant polynomials, so concentrated in 0, right? And so the most interesting part lies in degree 1, and so we look at the homology of CP infinity crossing infinity. So in principle, we have to worry about even dimensional classes, but it turns out that the cohomology really only appears in dimensions which are multiples of 4, right? And it was Morita who first computed these groups just by hand. So he wrote the best complex to compute these H1s, right? And this is the result. So we know the complete collection of Betty numbers, the rational Betty numbers for the classifying space of the diffeomorphism of the flow, right? You can try to relate these to Farrell's report, and in fact, this is an ongoing project with Ernesto. So we're trying to produce torus bundles over particular manifolds that are detected by all these cohomology classes. Okay. So this procedure works also for FT coefficients when P is not 2 and 3, right? So the only thing you care about is that the 12 can be inverted. And later on, inspired by the work of Morita, Furusawa, Tezuka, and Tequila, they computed the cohomology for the remaining primes, and they showed that the cohomology of the classifying space could be written in terms of modular forms. So, yeah, this is done using the classical Eichler-Shimura isomorphism. So now, what about non-orientable surfaces? I wanted to talk about. Well, so a non-orientable surface of G is by definition the connected sum of G copies of RP2, right? And you can define the mapping class group of such surface by looking at all diffeomorphism, the surface module of the component of the identity, like before. So there's no need to worry about orientation here. And here a couple of examples. So the case of genus 2 is the Klein borough, and the mapping class group is the work Klein group. In genus 3, the mapping class group is the group GL20. All right, and again, part of the same theorem of Nielsen learning tells us in the non-orientable case what is the homotopy type of the identity component and all the homomorphisms. For instance, in the case of genus 1, Diff zero of the projected plane is of the same homotopy type of result 3. In the case of genus 2, we're thinking of the Klein borough. The Klein borough can be rotated in one direction. Still, so it turns out that Diff zero in this case is homotopy equivalent to SO2, and Diff zero is contractible otherwise. Right? So you can try to think of characteristic classes of surface bundles, non-orientable fiber. Anyhow,
just let me ask you something, just to be sure.
yes.
For instance, to compute this, the homotopy type of this different this for connections, is there like some splitting along the exact sequence or something that otherwise how it would be done? Just to be sure.
If I recall correctly, what they do is they try to compare fibrations. Yes. So fibrations associated to this compact group with
And then you have just the longest homotopy sequence for vibration.
right. But you have to do it nice. You have to do it nice.
In this case, subgroup. SO3 is a subgroup.
They are.
So it's more than the homotopy type. It's a subgroup that has a homotopy type of the space.
Yes.
So the group structure is different.
Yeah, I suppose those groups act on the manifold. On the manifold, just that the rest is compatible. I see.
So now, you might think that there's so much information in the case of genus 1, for instance, because it's the result of 3 and the mapping group of RP2 is trivial. But then we can proceed to the case of marked points. So as I was saying, I like to play with the configuration space of k distinct points in a manifold, and this is by definition the space of n tuple of k tuple. Points in M, which are pairwise disjoint, right? So it's very clear that the symmetric group acts on this space, and we can think of the unordered configuration space. Well, SO3 acts by rotations on RP2, right? And thus it acts on configurations on the predicted line. So if you twist the universal bundle for SO3, you replace the fiber on the universal bundle by the configuration, the unordered configuration space. What you get is space which is a KG one. So you get an Hidber lane with one with the mapping class group as the fundamental group and no other homotopy groups. So then you get yourself a space whose cohomology is the cohomology of the mapping class. Then we can use the vibration associated to this construction to show that, for instance, in the case of F2 coefficients, the cohomology of the mapping class group of the projected plane with mark points is given as the cohomology of the SO3 and the cohomology of the unordered configuration space. In the case of F2 coefficients, if you're working with even dimensional compact manifold, then one can get at least additively the cohomology and the complication space from the very numbers of the manifold. So this gives you a complete answer in this case. So what about the Klein model? So we know by Nielsen and remain that if zero in this case is homotopy equivalent to SO2, right? And that the quotient, the mapping class group is C2 cross C2. So we try to play the same game, right? So we look at the exact sequence defined in the mapping class group here, pass to classifying spaces, right? So we have a calibration with fiber CP infinity. The basis is the classifying space of C2 and C2, right? So we have a spectral sequence with C2 terms given by the cohomology of C2 cross C2 with coefficients in the cohomology of CP infinity. And this time, well, because we're dealing with a fiber group, we better take into our coefficients. Rational coefficients wouldn't inform very much. Again, we're looking at twisted coefficients, and the way C2 cross C2 acts on this polynomial algebra is given like this string. So one generates that string element, and the other changes a sign.
What question is related to the question? The C2 cross C2, can you see the explicit creators of the forms?
Yes.
Which are?
One, so you present the Klein models as a quotient of a rectangle or a quotient of a cylinder, then one of them is reflection through an equator, and the other is
It has a lot of fixed points.
yes, and the other is a reflection associated with the action of O2 in the circle. And these two guys communicate. So yes, you can identify clearly what the generators are. And
it's a section, so this is
so I know what you're saying.
I just want to say this that it's a section of the quotient, so therefore Diff K is like a semi-direct product or something like that.
Yes.
K is it in this case?
Yes. Yeah. So that means a very easy description. So I mean, you could try to play the same game and write the integral term in this case with twisted coefficients, and why not? Why not? And it turns out that you can identify the algebra and you see that there's only one possible differential that decided the spectral sequence. You then compare with the spectral sequence of an easier vibration to say compare with this kind of vibration and the corresponding spectral sequence. And in this case, it's pretty easy to see that this differential is zero, and that proves the previous differential is zero. So now what you see is that since you can identify all these groups inside the different you end up showing that. So we ended up showing that the Diff K, the diffeomorphism of the Klein model was of the same homotopic type as C2 cross O2. And well, you have the same thing for you pass to classifying spaces, and then there's a similar theorem that says that if you look at this Farrell construction, where C2 times O2 acts on the Klein model, by diffeomorphisms, then this space is a KG1 for the mapping class group of the Klein model with markers. Okay? And you can get its cohomology in terms of the cohomology of this group and well, the classifying space of this product and the cohomology of the configuration space of distinct points in the Klein model. All right.
So So are you showing that Diff K is equivalent to C2 cross O2?
Yes.
Because you're showing it with the span space part,
Hmm?
but not as groups. Not with these.
Yes.
So it is stronger than
Yes.
It's at the level of groups.
Right. So you have, yeah. You have some group and equation is a homotopy equivalence. And then
You got
when you pass to the span space, you also have a homotopy equivalence. Yes. All right. So in some more recent work, a former student of mine, Nestor Colin, and I showed that the Nielsen resolution theorem holds in this case for mapping the groups of non-orientable surfaces with mark points. And we also show that the canonical projection, and this was with a mark point, does not admit a section, doesn't hold a section for large units. So the way one try to approach this is by looking at Klein surfaces. So Klein surfaces are modeled after Riemann surfaces, but apart from having analytical changes of chart, you also need complex conjugation, right? And this is the concept of Klein surface. So you can then talk about the analytic structure on such surfaces, and you look at the the set of all the analytic structure you can put on a non-orientable surface. Well, it can be orientable, but then in that case you're going to get a Riemann surface, right? And so you can define the concept of a map between the analytic between line surfaces. Also, given a different morphism of the surface, you can talk about pullbacks, right? Pullback structure in such a way that this different morphism is a morphism of a Klein surface, right? So in this setting, if you have Klein surface, an orientable double cover for that is going to be a Riemann surface, together with the unramified double cover and an evolution of the orientable surface, which is anti-analytic, right? So that this diagram commutes, and you get back your Klein surfaces by your Klein surface by pushing out the orientation, the orientable cover by evolution. And well, it turns out that if you have a different morphism of this non-orientable surface, and it fits escape point, then it admits exactly two liftings to the orientable double cover and preserving two K points, right? And this choice induces a map at the level of mapping class groups. So you can inject the mapping class group, the non-orientable mapping class group with K mark points into the orientable one with 2K mark points. And so this map is going to be injected in the case of G is greater or equal to 3 if you don't have mark points. And it's going to be injected for every genus if you have at least one mark point. Right? So you can talk about you can try to mimic the definition of the Hidber space in the Klein surfaces. Namely, you think of two analytic structures and say the Hidber equivalent if they differ by pullbacks by diffeomorphism, which is isotopic to the identity, right? And then the technical space is nothing but a portion of all these Klein structures, the analytic structures, modulo Diff 0, right? And again, in the case when the surface is orientable, so you get back the classical statement that says that the technical space is homomorphic to R6G minus 6 plus the number. And you have the roughly the half of the dimension in the non-orientable case, right? Also, this orientable double cover induces a map of the corresponding technical spaces, as like this. So if I the projection, then this induces a mapping by pullbacks, right? Sending a Klein and the analytic structure of energy to the class of the pullback on the double cover, right? And we know what the image of this map looks like. Basically, the space or the cell, the space of complex structures in the double cover, which are fixed by the pullbacks by the evolution. So now, to show the Nielsen transition theorem, so we know this that we have two maps. So we have an inclusion of the mapping class group of NG into the mapping class group of S G-1 with the double number of mark points. And we have this mapping used at the level of technical spaces. So we know how these maps behave among themselves, and we can use this relation to show that every finite group of the mapping class group of the non-orientable surface acting on the corresponding technical space has a fixed point. So now the thing is not difficult. So you start with your group in the mapping class group of the non-orientable surface. You lift it to the mapping class group of the orientable surface, right? And add up the class of the involution. So the image of G and the class of the involution generate a group in the extended mapping class group. And I'm calling H here. It turns out that G and the class of involution commute in this case. So H is nothing but G times C2, C in the extended mapping class group. And so now we use the Nielsen substitution theorem for the extended mapping class group. And that's basically that. So I mean, thanks to the way we describe the image of 5-star, right? We know we can find. So we know there's a fixed point in the technical space of the orientable double cover for this group H, right? And being a fixed point, it has to be in the image of 5-star, and the structure, the analytic structure hitting that is the one that is going to be fixed. Well, that's about it. So how do we look at the non-existent exceptions? Well, we use characteristic classes, right? So so the story goes as follows. Suppose that you have a bundle Z from E to B, and that is a bundle, smooth bundle of surfaces, right? So you can pass to derivatives, right? and get a map from the tangent bundle of V to the tangent bundle of V, and look at the kernel. Okay? So this is the so-called vertical bundle, and it's going to be a two-dimensional oriented vector bundle over E, right? And as such, it has associated an Euler class. So from this Euler class, one can define the so-called Miller-Morita-Mumford classes for this bundle. Namely, you take the Euler class of the vertical bundle, write it to the power n equals 1, and look at the image under the Giese homomorphism. So that lands in H2n of B, of the base, right? And well, you can do that for any smooth bundle. Now you can play this game using the universal bundle. You get your Miller Morita-Mumford classes for the universal bundle, and then you have any bundle which is gotten as a pullback to the universal one, then you get by pullbacks characteristic classes for any such surface bundle, right? So I already mentioned this, that these classes can be seen as cohomology classes of the these kappa classes can be seen as cohomology classes in the Russian cohomology of the mapping class group, and this is a stable isomorphism. G tends to infinity, and there's still another approach to look at this. So it turns out that there's a stable map called the Becker-Gaussian transfer that goes in the wrong direction from the suspension spectrum of the base to the suspension spectrum of the total space, right? And that satisfies certain nice conditions related to the Euler characteristic of the surface. Anyhow, in the oriented case, what you can do is check that this the induced mapping cohomology by transfer is given by the Giese map applied to X times the Euler class of the vertical bundle. So there's a way to define these Miller Morita-Mumford classes in terms of this transfer and the Euler class, and in particular, if you look at even dimensional ones, so this is class the dimension 4n, right? These are gotten as images of the transfer of powers of the first contracting of the vertical bundle. All right. So so we can use this as this observation as motivation to define classes in the non-orientable case, right? So suppose that you have a non-orientable surface bundle, right? And you can look at the vertical bundle again, look at the first contracting class, and then take the I power and look at the transfer, the map induced by the transfer in cohomology. So these classes look naturally, they lie naturally in dimension 4i of the base. And if you do this for the universal bundle over VD of NG, then you can get characteristic classes for any non-orientable surface bundle, say smooth over a manifold X. Okay. So thanks to the work of Natalie Wall, Soren Galato, Madsen, and others. So we also know that these classes give you the rational cohomology of the mapping class group a stable mapping class group in the non-orientable case, right? And thus in particular, we know that these zeta i's, which lie in the dimension 4i, are non-zero if the genus is big enough. So in this case, greater or equal than 16i plus 3. All right. So how do we prove the non-existence of a section? So what we do is first show that if you look at the projection from the diffeomorphisms of the surface to the mapping group, and we use the discrete topology, so we're looking at the homomorphism of the string group, then the image of these zeta i's are zero in the cohomology of the Diff group. So we use this, and then apply this property, right? That the CIs are non-zero in this dimension. So so if there was such a section, then these composite would be the identity. So the corresponding composite cohomology would be the identity, right? And then the way the dimension were chosen give you the right range for these things not to happen. All right. So now, one thing also to look at cohomology, and what we look here is look at the Farrell cohomology of these mapping class groups. The mapping class groups can be very big, right? The groups of finite feature cohomological dimension, meaning that all of them contain torsion-free subgroup with finite index, right? And the cohomological dimension of such torsion-free subgroup is by definition the virtual cohomological dimension of the group, right? So one defines a Farrell cohomology of subgroups as kind of generalization of the Tate cohomology for finite groups. So we do this by using a complete resolution for these groups. And well, so what we know is that these Farrell cohomology groups coincide with the usual cohomology in positive dimensions. They're zero if the group is torsion free, and so these are torsion groups, right? So you can study them by looking at the p prime component one prime at a time, and it's a nice feature that some of them admit that they have periodic cohomology, right? And in that case, there is the so-called Brown formula that gives you the p prime component for the correct cohomology of these groups in terms of the homology of the normalizer of the CPs inside the groups. So you count the number of 62 subgroups of order P. You actually look at the conjugation facet of such subgroup, take the product of all the cohomology of all those, and that recovers for you the Farrell cohomology, the p prime component of the Farrell cohomology object group. All right. So now,
Equal and the period is related to what? The period or the Diff cohomology. The D. The cohomology I.
So what I was saying that, I mean, see the torsion, so you can look at the private components one at a time, and then assemble them to get the.
Yeah, the one before. You have that is periodic.
Yeah, you don't always have that piece.
Exactly, but if it's periodic, it's usually some geometric reason that the cohomology is periodic.
Well, there are some criteria, and
I thought it was related to the end, the virtual homological dimension. Doesn't matter.
yeah. So basically, you have to find an inverted model and a cohomology that gives you the periodicities. Right. 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 And but what makes these guys computable is this nice Brown formula that gives you the pre-primary component of the homology in terms of the cohomology of all these normalizers, the CPs counted by conjugacy classes. All right. So so now in the case, in the periodic case, there's a nice way to get the period, and it goes as follows. So say that you're looking at this group gamma, right? And you have, I mean, being a group of finite neutral cohomological dimension, you know that it contains a torsion piece of group delta, right? So any torsion subgroup of gamma can be identified with a subgroup of the quotient gamma by delta because there's no torsion in delta, right? And if you're looking at if you think of pi as a cyclic group of order p, then well, you better we will have a way to relate the cohomology of gamma with the cohomology of pi or C mod p, right? So the mod p cohomology of pi in this case is an exterior algebra of first dimension class or one-dimensional class times a polynomial algebra on two-dimensional class U, right? And it turns out that if you look at the restriction, right, from the cohomology of gamma to the cohomology of pi, and follow these by the reduction of p, then you land in the polynomial component, right? So that it better be maximum power of U, and which is called n in this case, so that the polynomial algebra generated by this power also contains the image of the restriction followed by the reduction mod p. So these ends are related to the period in this way. If the gamma is a p periodic group, then the p period can be computed as follows. You look at the lowest common multiple of 2 times these ends for every. So we will release pi runs over of all overall single pieces again, right? And it's a recent result of Nestor Colin, Rita Jiménez, and myself that when the genus is greater than 2 and p is a not prime, then if the mapping class group of these non-orientable surfaces with mark points contains p torsion, then the p period is 4. And well, the idea to show one of the inequalities in the following. So say that you start. So we're looking at mark points, right? Say that you have one mark point in the mapping class group, and So you look at a symbol P pi inside the mapping class group. You can lift it to the diffeomorphism by the Nielsen organization theorem, right? So this is a symbol P that acts by diffeomorphism on your surface, and that fixes one point. So thus it acts on the tangent space to that particular point. So the map that sends any such diffeomorphism to its derivative gives you a representation into the tangent space, and it turns out that it lies in the orientation preserving isomorphisms of the tangent space if you choose an appropriate orientation. So now you can pass to classifying spaces and cohomology, and we know what happens with in cohomology between GL plus and GL2 plus and GL2, and the thing is that well, there's a contrarian class which is in dimension 4 that hits the square of the Chen class, VGL2 plus, right? And thus, this contrarian class produces a class in the cohomology and mapping class group that goes to a non-zero class in the cohomology of this C mod P, right? So this number we were hoping for here is this 2 times 2 is 4. So that gives us an inequality. So the P period is going to be greater or equal to 4. And we also can show the other way around. And the way we do that is by we look at the so-called fixed point data. So there's some combinatorial information attached to all these diffeomorphism fixing points in these non-orientable surfaces. But then the result is that this mapping class group contain a subgroup of the P, even only if the Riemann-Horowitz equation written here has a linear solution with those subject to those restrictions, and two that for all genus greater than 2 and all primes P, if the mapping class group of your non-orientable surface has P torsion, then it has periodic cohomology. And so next we have a way to count all these normalized of these conjugacy classes of single beats inside your mapping class group, and probably better to end up with an example. So the example is the case where the genus is equal to P, and in this case, well, you have only one solution in the Riemann-Horowitz equation, and so in this case, it turns out that the normalizer of these C mod P's are Hilbert groups. The cohomology of those is very well known, and this tells you via Brown's formula the cohomology, the correct cohomology of the mapping class group. Again, for genus